When initializing Dijkstra's algorithm, we initialize two vectors. First, a vector distance that contains the combined weight between the origin vertex, in this case the vertex containing the data value 4, and all the other vertices in the graph. We initialize all these values to infinity. The second vector is the set of parents. We use this to keep track of where the parent is coming from, so that way we can determine the actual shortest path. We then initialize a priority queue, and then FP here is how we're going to take the parent and use a stack to be able to keep track of the final shortest path, as we will see. So when we initialize, what we're going to do is we're going to evaluate at the initial vertex and look at the outgoing edges. We see that the outgoing edge from 4 to 5 with a weight of 1 is less than the edge from 4 to 20 with a weight of 3. So therefore, when we put it into the priority queue, we see that the vertex containing 5 has a higher priority because to this point, it's the shortest path. Now, there's no guarantee that that's the actual shortest path, but here we're using dynamic programming to potentially improve our approach. And when we see that we will evaluate at vertex 10, that we will actually be able to prune the search tree. The way Dijkstra's algorithm works is that we will have the distance updated for these two vertices. In this case, the distance is 1 and 3 respectively. We also have parent of the vertex containing the data value 4 for each of these. So now we're going to evaluate from the vertex containing 5. The thing we need to bear in mind is if we encounter a vertex that we have already encountered, then the distance u plus weight is less than the current distance, then we update the weight and the parent. This is why it's important to initialize the values at infinity, because initially, if the distance is infinity, or in this case, the largest possible signed integer, then these values initially will automatically beat it. Otherwise, we have to beat this current total distance in order to update the value. Well, if we don't update the total distance, we just don't evaluate this again. So now let's evaluate from the vertex containing 5. We have one outgoing edge to the vertex containing 10. Previously, the weight is infinity. But now we compare the weights. We have the previous weight at 5, which is 1, plus the outgoing weight, which is 5, which means it's 6. 6 is less than infinity. So what we're going to see in the next animation is that the parent of 10 is going to become 5, and the weight at 10 is going to become 6. So now we're going to put this in the priority queue, and we see that we are going to evaluate 10 here. 10 has one outgoing edge to 18. So what we're going to see is that 10 will go to 18 with its current weight of 6 plus 2, which is 8. And now we have found a path. And currently, 18's parent is 10. What we will see with Dijkstra, and why this is a useful algorithm, is that when we get back here, we're going to find that there's another path that beats it. This will allow us to update it, and that current path hasn't been evaluated yet. And we see that just because something is a shorter path in the short term doesn't mean it's going to be a shorter path overall. But now let's keep going. So now we remove 5, and now we're going to evaluate from 20. So from 20, what's going to happen is we have two outgoing edges, 10 and 30. The current weight at 20 is 3. So 3 plus 4 to 10 is going to be 7. But we can reach 10 with a weight of 6. So therefore, we should not replace the parent. But see, the benefit here is that 20 is going to be the parent of 30, because 30 is currently infinity. So what we're going to see is that 30's weight is going to be 3 plus 2, which is 5, and 30's parent is going to be updated to the vertex containing 20. So now when we evaluate 30, we have a current weight of 5 plus 2. Now we evaluate 18 again. Because we can reach it in 7, what we're going to see is that this is going to be updated from 8 to 7, and 18's parent is going to be 30. Because of this, we have now found a shorter path than we previously found. We see that's exactly what happens. So now we have evaluated all of the edges, and now we start at the distance. We now know that the shortest path to vertex 18 from the vertex containing 4 has a weight of 7. But what is the shortest path? We start with that vertex, and we see that its parent is 30. And so now we're putting it onto a stack. So now we've used a priority queue, a vertex, vectors, nodes, and edges, which are pointers, and C++ structs to be able to solve this problem. 30's parent is 20, 20's parent is 4, and 4 is the origin. So therefore, when we pop them all off the stack, we would follow this specific path, which is the shortest path.